Physics time. Today we're talking about momentum and impulse.
Momentum, I'm going to need a new marker, I can already tell. And impulse.
The momentum part should be fairly easy. We have this equation for momentum. P equals m cross v. Do you remember cross product a little bit when we talked about vectors when we were watching that video about vectors? And this cross product means that the force that is causing this momentum, because another way that we express momentum is P equals delta F over T. You'll see that the units work out. Because remember, force is measured in newtons, kilogram meters per second squared. If we divide that by time, we end up with kilograms meters per second, which is also mass times velocity. So these two things, in fact, this is how Newton described momentum. I think, I might be wrong. I think he might have described it the other way around. He described force as a change in momentum times time. It doesn't really matter. Either way, whichever way Newton described it is fine. But these are our two equations. Your book doesn't even render this one, but this is just another way of thinking about it, kind of. But this cross product means that the force causing this momentum and the velocity have to be in the same direction, and to whatever degree they're not, we use the cosine of the angle theta between them. So let me use an example because I think it'll clarify it a little bit. You can calculate the momentum of an object with its velocity, but if the velocity and the force are not in the same direction, we'll do this more when we do work, we have to use an angle measure to get between them. So for now, just recognize that this cross product is times cosine of the angle theta between them, okay? When we get to work, we'll do actual math with that. And when I say work, I mean not the work we're doing for this chapter, but when we get to the physical concept of work, which is force times distance, we will talk more about this then. For now, when you calculate momentum, you'll just use mass and velocity. Only moving objects have momentum. Why would that be, mathematically? Yeah, what if the velocity is zero? We describe that in reality, that the object is stopped, and it's not moving. If the velocity is ever zero, what will the momentum necessarily be? Zero. What if this is the mass? What if this is a 3 million solar mass black hole? 10 to the 100th kilograms. That's probably a bit of an exaggeration. But the velocity is zero. What's the momentum? Yeah, it doesn't matter. Any number times zero is zero. So the momentum must be zero if the velocity is zero. We also have this equation for impulse. J equals Ft. Or more specifically, we can also use J equals delta P. These are both for impulse. And an impulse is something that you may not have. Well, the word impulse is sometimes used like you had a drive to do something. Like I had an impulse to drink my tea. Tea. Impulse. Or like the impulse buy section of a grocery store where you're standing there waiting in line and they have all the candy and beef jerky and toys that you might have for your forgotten children. Those impulse buys are things that you do kind of spur of the moment. That's how we generally use the word impulse. But in physics, we're talking specifically about a change in momentum, which is also a force times a time. You need to know both of these equations because sometimes you'll be given momentum or mass and velocity, and you'll need to use this one, and sometimes you'll be given a force and a time. One of the ways that we describe impulse, and let me return to momentum for a second. Remember, only moving objects have momentum. And so, therefore, if we have a momentum, these objects must also be moving. The example that your book gives, and I really like this example, and I'm also going to grab my pillow real quick. I have to make sure I switch this picture in picture. I have a pillow here. This is my pillow. This is the pillow I use to sit on the radiator when it's time for me to look out the window forlornly. And here I have some chalk. Yeah? I'm going to drop both of these pieces of chalk like this. And you already know what's going to happen. because your instinct tells you, I don't think you would be able to describe this physically or certainly not mathematically, but your instinct tells you what's going to happen to these two pieces of chalk.
Fall.
They're going to fall. Okay, good. That's not what I was looking for. When I drop them, one on the pillow and one on the ground, what's going to happen to these two pieces of very expensive Hagoromo chalk? Which one will break?
The one on the floor.
The one that's going to land on the bare floor. Why? Because there's a more force on this one? No, we're assuming these have the same weight. Probably not a super safe assumption, but we're assuming these have the same weight. There's not more force on this one. So what's the difference?
Hardness surface.
Okay, yeah, you're saying the hardness of the surface, but we'll talk mathematically about why that is in a second. Let's see what happens. Kablooey. Yeah, look. That one did break. It only broke a little bit, which is good because that's the world's best chalk. And the one on the pillow didn't. The example your book uses is that in this picture down here, I'm so bad at getting this to show to the camera. In this picture down here, a car with a certain force is running into a hay bale. And in this picture up here, the car with the same force is running into a wall. And you already know, once again, instinctually, what's going to happen. But the way that we describe this is with impulse. In the case of the car and the hay, or the case of the chalk and the pillow, what of this equation, we're talking about this equation now, what have we changed? Time. That's exactly right. It's got the same force. We're going to assume it has the same force of impact. But in the case of the pillow or the hay, it's increasing the time that's in contact. So basically, it gives it more time to slow down. It gives it more time to decelerate, to stop. Whereas with the hard surface, there's very little time. The other example your book uses is this one of rolling with the punches. You know what it means to roll with the punches? As a phrase, that means if something bad is happening to your life, just kind of go with it. Don't put up too much resistance. In boxing, I'm not, as you can probably tell, a major boxer, but in boxing it means that when the guy is punching you, you move back away from the punch. Not because you're scared or you're a coward or because it's going to stop the punch from hitting you, but in this context, what does it do? As you're moving in the same direction as the punch, what is changing?
More time.
Yeah, it gives it more time. It gives it more time. And therefore, in that case, it does reduce the force. We have a set impulse. Your momentum is going to change a certain amount. And in that case, more time means less force, which means fewer broken teeth. What about if you're a really bad boxer and you're always leaning into punches?
More broken teeth.
More broken teeth, more broken noses, more broken skulls and concussions. The unit then for impulse is what? If we look where J is impulse, F is force measured in newtons, yep. Force measured in newtons. T is time measured in seconds. So then what's the unit for impulse? Newton seconds. Newton seconds. Newton times seconds. Newton dot second. We didn't really do this thing for the momentum, but let's do it now. P is momentum. M is mass. Cross is cosine of angle theta. V is velocity. Velocity is measured in meters per second. Mass is measured in kilograms. Cosine of angle theta, not measured in a unit. And the momentum then is kilogram meters per second. So there's kind of like a intricate relationship with these where force and time are momentum, force and time are also impulse, but mathematically different. Impulse is also change in momentum, and momentum itself is made of mass and velocity, which mass and velocity divided by time would be force, because the velocity divided by time is acceleration, mass times acceleration is force. So there's an intricate relationship between all of these things, and when one changes, the rest change. There's I really enjoy the section of your book called bouncing, so I'm going to make a little section here to bouncing. Bouncing is one of the fun parts of physics. Bouncing is interesting because if you think about it, physically, what's happening when something bounces? Yeah, it's not only falling or putting a force on an object, but it's also having a force put back on it such that it then moves the other direction. Let me get some bouncy balls out here. Here's my racquetball of science, which also is a pantyhose racquetball of science. But you can see pantyhose racquetball of science. I'm going to try to drop it. I'm going to switch it back away from picture-in-picture for a second so you can see this. Drop it. bounce. Let's describe that. So here we have the ball is falling.
Fall, hitting those fall.
And then as it hits, it's going to put a force on the floor, and the floor is going to put a force back up on it. But that's not all. The force that goes back up on it will, in this case, deform the ball a little bit, compress it, and now it has some elastic potential energy. And when that elastic potential energy is released, it applies a force back up on the ball. And will the ball ever reach the same height it did when you dropped it? Not ever. It can't. Why? How is the energy, we haven't talked about energy yet, but how is the energy lost when this ball falls? Several ways. What's one? Yeah, but what does the energy become instead of turning back into kinetic energy? So some of it is lost to the chemical bonds, the chemical potential energy. Basically, some of it is lost as this ball expands and contracts when it bounces. Some of it is lost to friction between those molecules, or surfaces. Maybe regions of the ball would be a better way to say it. What else? What else do you notice when it bounces? But that's not how the energy is lost. What's another way the energy is lost?
Drop again, just make sure.
I'm doing this.
Sound.
Sound. Yeah, some of the energy is lost by causing the floor and the air around it to vibrate. And that energy comes from somewhere, and that coming from somewhere is from the bouncing. And another way is in the actual friction of the contact. Both the floor and the ball are just a tiny bit warmer. They almost immeasurable, probably a truly immeasurable amount warmer than they were before. So that energy is lost. The ball will never regain its complete height. Unless, how can I make it? If I want to make sure I catch this ball in my hand.
Throw.
Yeah, I can throw it, and now it goes even higher. Why?
You add more energy.
I'm putting more energy. I'm changing its momentum more. I'm giving it more speed. Am I changing the mass at all? Remember, momentum is mass and speed. No, but I'm giving it more speed, and therefore more impulse, and therefore I can make it bounce higher than it. Hey! Pantyhose ball. Now, thinking about impulse as change in momentum, which has a greater, for a given mass, or let's say for a given weight, that's a force, and a given amount of time, right? So a certain J, which one applies a greater force? One that bounces or one that doesn't bounce? Sometimes I do this, actually I could probably do it with my pillow, because this probably won't bounce. Which one will apply more force?
Pillow.
The ball. Why?
The ball.
Let's pretend they're the same mass. Let's pretend they're the same mass and density. In bouncing, which this one does, the impulse is bigger because the delta P, it's not only changing velocity to stop, but changing velocity to go back. So let's say, this will be very simplistic, but let's say it was 2 meters per second down, and now it's moving 2 meters per second up. What was its change in velocity? Well, if this one was only moving 2 meters per second down, let's say it has a mass of 1 kilogram. That'll make the mass easier. What's the change in momentum here? From 2 meters per second to 0. What's the change in momentum? Yeah, it's 2 meters per second. It's a change in momentum. What if now it was going 2 meters per second down, and now it's going 2 meters per second up? What's its change in momentum? 4 meters per second. It has twice the impulse. Sorry, I erased that with my sweater. A bigger delta P. Because the other way around. This one has the bigger delta P because it has a reverse velocity. It's change velocity. So basically your book says something like, if you have to get hit in the head with a baseball bat, make sure it doesn't bounce. Which would you rather, I think this might even be in your chapter review, and if it is, I'm giving you a problem. No. If they're moving at the same speed and they have the same mass, then yes, that is the case. Do get hit with one that won't bounce. So let's say you're standing, this is you. I'm going to draw a picture of you with your with your freaky Henri Matisse style of leg. This is you. And above your head are two shelves, two rickety old shelves. One has a 1 kilogram flower pot on it. It's growing another person. You're in a spooky place. 1 kilogram. And the other one has a 1 kilogram basketball on it. Now they have the same mass, they're going to fall the same distance. Let's say they're falling the same speed when they hit you. Which one would you rather be hit by?
Basketball.
It seems like the basketball, but you're wrong, because this one will impart a greater impulse because it's going to bounce off, right? Then the same way that the bouncing one had more impulse here, the bouncing one will have more impulse here. The flower pot will, the energy that the basketball is going to use to knock you even harder on the head is going to be lost in the flower pot because of braking. A way that I demonstrate this in the past, and it worked somewhat well, but I don't have the stuff to do it today, is we find, give me a second. This has betrayed me in the past, and it's never really worked super great, but I'm going to try it again. In fact, I bought these balls because they don't bounce. I'm going to point this at the door. We're going to make the wild assumption that these two things have the same mass. It's probably not far off. Squishy ball, racquetball, okay? We should find that the one that bounces imparts a greater force on the door. How am I going to measure the force on the door? Very rule of thummy, very, don't say thummy.
How much the door moves.
Yeah, how much the door moves is what we're going to do. So I'm going to throw with my right hand, both of them. I'm going to try to apply the same force. This is all very fly by the seat of your pants. I'm going to try to, you're not in it, Justice, don't worry. Sticky ball, non-bouncy ball. Great. Let me try again. I'm going to aim at the side of the door because you know it's going to make a difference whether it hits here or here, obviously. So I'm going to try to aim at this part of the door. Now that I've called my shot, it's going to be really embarrassing when I do not in any way hit it. Nice. Okay, racquetball. We got a couple of bounces there, but you saw the door move a little bit more, right? Justice, just you did. Let's do it one more time because it is kind of fun. So the idea of impulse, we're not really so much worried about the force. They should be applying the same force. But the idea of impulse is that one of them is going to be changing the momentum more than the other because of the bounce. And because of Newton's third law, when this one, hopefully, offers a greater change of momentum to the door should move a further distance. That's what we're hoping to see. And I think we did see it, but someone said no. Okay, here we go. Was there a little bit of movement? Maybe, but a very little. I think there was more movement in the racquetball one, don't you? I'll put that part of the video on slow-mo. Or, no, you viewer, I don't know how to do what I just said, so you viewer, switch it to like 0.25 and see what's going on. I've got to get the camera back. Come on, camera. Also, switch this part to or to 2 times because you don't need to. If you already have your hand on the speed adjuster, you don't need to watch me adjust the camera for 25 seconds. You can watch for 12.5 seconds and consider yourself lucky because we all had to live through that. There is one of the fundamental laws of the universe. We have the law of conservation of mass, which we've talked about before, and there's also it always has existed, but now we're going to talk about the law of conservation of momentum. There are 3 fundamental conservation laws of the universe. They are the law of conservation of mass, which really I should say the law of conservation of energy, because those 2 things are equivalent, and energy, maybe I shouldn't say equivalent. Those 2 things are intricately, necessarily related, and energy is the more basic thing. Then the law of conservation of momentum, which we're talking about today. There's also the law of conservation of angular momentum. That is how much things spin. So the law of conservation of momentum, tells us that in a collision, momentum is always conserved. There are 2 kinds of collisions. What are they? Tatum, you did your lab on this. Inelastic and elastic. Big if true. It is true, and it is big. In an inelastic collision, what happens?
Inelastic, they stick together.
Yeah, they stick together and move as one object afterward. Stick together and move as one after. In an elastic collision, they bounce. Yeah. Bounce. And in this one, they swap momenta Momenta is the plural of momentum. So a fool might say momentums, but the actual plural is momenta.
Plural momenta.
In this one, they swap momenta. Now, does that mean they're necessarily going at the opposite speed of each other? Well, let's check this out. Here we have a billiard ball. Let's say, unlike in reality, the cue ball is slightly smaller in diameter and has slightly less mass, I think less mass, than the other billiards balls. But let's say these two things have the same mass. They have some mass m. When they collide elastically, this one has some velocity v, and this one has some velocity v prime. After the collision, now this one, since they have the same mass, now how's this one moving? It switches with the other one. So now this one has velocity v prime, and this one has velocity v. That's an elastic collision. Now, what if this one has velocity 2m, still at v prime? Well, now the one with the smaller mass will have a 2v prime, and this one will have, what do you think?
1/2.
2m. Yeah, 1/2 v. They still switch. It's just a factor of they're inversely related to their mass. In an inelastic collision, this one is like, the classic example is trains. This one has mass m. They're going to collide. This one has mass m. They're going to collide. If they both have the same velocity v and the same mass m, after the collision, what's going to happen?
Oh, they're going to stick together. So
Stick together, and the velocities will do what in this case? Yeah, but one's positive and one's negative. Sorry, v prime. They cancel each other out. Yeah, they will. But how does that not? Now listen here. This is the main and the last thing we're going to talk about for the law of conservation of momentum. V equals 0. They're hooked together. How does this not violate the law of conservation of momentum? They had speed before, and now they have 0 speed. So they had momentum before, and now they have 0 momentum. How does that not violate this law? Where did that momentum go?
It's because they have big mass.
No, their mass didn't increase. And now they have 0 momentum, so that can't be it. Where did that momentum go? Kind of like where the energy went when my ball bounced. Sound. Some of it is lost to sound. This would make a big noise. Some of that momentum is lost to the air molecules, which have a very little mass, moving faster. They have a greater velocity now. Some of it is lost in the same way, but to friction. Now, those little particles that have that had some velocity and very little mass now have a lot more velocity. They're moving faster and therefore more energy. Therefore, they're hotter. So this is always true. Sometimes in physics we say things like, oh, this is true, but not friction. Don't worry about friction, and that's true. But this is always true. The momentum now just changes to be the momentum of particles. It increases the heat and sound of the system, which have their own momentum. Is there sound in this collision?
Yes.
Yeah, it's not going to be as loud as a train crash, but there is sound in this collision, and how does that show up as loss? Well, this one won't quite be 2v prime. This one will be like 2v prime minus however much was in sound. This one will be half v minus however much was in sound.
Big if true.
It is. Questions about any of this?
No.
For some reason, that didn't go.